3 to n equals 1. All right. So we know the delta E atom okay, the absolute value of it is equal to hc over lambda. Okay. And we know that that's equal to 2.18 times 10 to the minus 18th joules. And n initial is what? All right, it drops down from 3 to 1. So what's our initial state? It's going to be 3. So it's going to be 1 over 3 squared minus 1 over 1 squared. All right, and we will take the absolute value of that answer. So plugging this number in, we should get something like, it would be the absolute value of negative 1.94 times 10 to the minus 18th joules. But we're taking the absolute value of this because the photon wavelength can't be negative, right? So, okay, from this we can say that lambda is equal to hc divided by the absolute value of delta E atom. Let me just erase this arrow. Okay, so it's going to be 6.626 times the speed of light, 2.998 times 10 to the 8th meters per second. All right, and you divide all of that by the absolute value of negative 1.94 times 10 to the minus 18th joules. Let's look at what cancels here. So joules cancels, seconds will cancel, and you get meters. So what you'll end up getting is what is this? 1.03 times 10 to the minus 11th? No, minus 7. And the unit will be in meters. In nanometers, what would this be? So it's 10 to the minus 9th nanometers per meter. All right, so it'll end up being 103 nanometers. So what I did was I calculated the changing energy of the atom. It's negative because the electron is dropping down and emitting a photon, so the atom's losing energy with that photon. And then I'm solving for the lambda from that. Does 103 nanometers make sense? And the answer is yes, because X-rays have very short wavelengths, get a very high in energy. So you don't have to work with these equations to get used to them, but hopefully with some problem solving, we'll get there. Okay. Questions so far? All right. You're probably like, man, this is mind-blowing stuff, but it's actually not too bad. All right. It's just energy of a wavelength of light, hc over lambda. That's the same as the delta E of the atom. Okay, solve for the wavelength from that relationship. And again, it all comes from the shells. Okay, how would I label delta E atom in that diagram? Going back to this, where would delta E atom be? Well, I'll give you an example. Okay, here's delta E atom right here. Alright, that's equal to Hc over lambda. If I want to solve for the wavelength coming off of this atom, it's Hc over delta E atom. Make sense? I'm just doing some algebra. Sometimes delta E atom is negative, right? When the electron's falling down, okay, from say 3 down to 1, for example. If I was doing 3 down to 1, delta E atom would be that, okay? So for this problem, delta E atom is this. But because wavelength can't have a negative number, we just have to take the absolute value of it. Okay, and that's what we calculated there. So do you see how the Bohr orbits relate to the equation and the calculation? That's what I want you to see. Cool? You're all, yeah, we're 50% there. Still another 50%. All right. All right, so that's electrons. But here's the thing. In the late 1800s, Thomson discovered the electron, and he was able to measure the mass-to-charge ratio of the electron. That's assuming that electrons behave as particles. Okay. So here's the thing. If light is quantized in its energy, and it also behaves as a wave, and electrons are also quantized in their energies, do they also behave as waves? Right? And that was the question of the day. And a thing that Bohr's model doesn't really explain is, how come electrons don't just fall into the nucleus and self-implode? Right? You know, why don't electrons just like fall into the nucleus and the atom just neutralizes itself and ceases to exist? Why does that happen? Okay, and so it turns out that this story continues, and what we have come up with in the 1920s, we started to come up with the actual study of quantum mechanics. And it all started with this idea that electrons behave as waves, not just particles. If an electron exists as a standing wave around an atom, how can it fall into the nucleus? If it's here relative to the nucleus here, whether it's here, or here, or here, it's everywhere, okay? Electrons exist as clouds of electron locations, not so much a single particle that's going to fall into the nucleus. Okay, and so the birth of quantum mechanics helped explain why we don't have electrons that just fall into the nucleus and dissipate. Okay, and that's why this story is so darn cool. You know? Louis de Broglie in 1924 proposed that electrons behave as waves, not just as particles, and they have certain wavelengths or wavelengths that are allowed versus others that are not allowed. And so if you have this electron moving around the nucleus of the atom as a wave versus a certain other wavelength where it's not allowed and it might collapse in on itself, we have certain wavelengths of energy that are allowed versus those that are not. Okay, so this is how this, relates to the energy of the electrons in an atom. Right, so if the electron has a certain wavelength to it, its energy must be quantized, and it can only inhabit certain distances from the nucleus to make the wave not close in on itself. Okay, and that's how we get these Bohr orbits that have certain distances from the nucleus in discrete quantities. Okay, so without the right wavelength of the electron, allowing it to occupy an allowed distance from the nucleus, we wouldn't have quantum theory. We would not observe this. So most people think of an electron as orbiting a nucleus, just like planets orbit the sun. Okay, but now imagine the way the electron encompassing all around the atom all at once and behaving as a wave. Okay, so if I was to run around the classroom right now like an electron, okay, and you were the nucleus, instead of running around the classroom in a circle, I'm going to get my exercise for the day. Instead of running around the classroom in a circle like this, instead, I would start being the wave around the nucleus. Right? I would start doing that. And imagine an electron moving so fast while it's doing this that it encompasses all around the atom all at once as a wave. Okay. So maybe it wants to fall into the nucleus, but then because it's a wave-like particle, it moves away from the nucleus before it can ever fall into the nucleus. Okay. Whew, man. All right. Has anyone ever seen the original Superman movie with Christopher Reeve? Probably not. It's an old movie. But he flies around planet Earth really, really fast at one point. Imagine the electron moving so fast that there's no way you could ever infiltrate into the nucleus of an atom without getting hit by that electron. Right? It's everywhere and nowhere at the same time. Really weird stuff, but that's what's happening. Okay? That's the model, at least. So de Broglie came up with this equation to describe... Yeah, I gotta catch my breath. All right. So de Broglie came up with this equation to describe not only the wave nature of electrons, but he said, well, you know, if electrons behave as waves, other microscopic particles can also behave as waves. And even macroscopic particles have wave nature to them. You have a wave, I have a wave, everything has a de Broglie wavelength. It's just that the de Broglie wavelength for large particles is so small that we don't notice it, you know, but we're all kind of vibrating in place, sort of. Okay. So you can ask your friends, you know, what's your de Broglie wavelength? All right. So the de Broglie equation is wavelength is equal to Planck's constant divided by the mass times its velocity. Okay. So here's a sample problem. What is the de Broglie wavelength in nanometers associated with a 6.2 gram ping pong ball traveling at 15.6 meters per second? And it says, note that 1 joule is equal to a kilogram meter squared per second squared. So here's that, you know, that calculation again, that conversion. Okay, so lambda for the Broglie wavelength is h over mu. This is pretty simple, but just to show a plug and chug. (6.626 to the minus 34 joules times seconds). We're going to go ahead and use this conversion of 1 kilogram meter squared per second squared equals a joule. And since we want this in nanometers, we know that we want 10 to the 9th nanometers equals a meter. And all that divided by 6.2 kilograms, excuse me, 6.2 grams. And we know that there's 1,000 grams in a kilogram. And the velocity was 15.6 meters per second. So plugging in all the numbers in there, let's look at the units. Grams cancel, kilograms cancel, joules will cancel. Let's see. If I move this s to the minus 1, seconds to the minus 1 up in the numerator, it becomes a positive 1, which means times second here means second squared, which cancels out this second squared. Okay, so it's ultimately like saying s times s to the minus second. All right, this is just how the seconds work. It's saying s times s now. Oops, there's no more, nothing at the bottom anymore. So 1 plus 1 is 2, minus 2 is 0. So all this cancels out. Okay. And then of course you get meters here, which is the same as canceling out one of these meters up there, and then this meters here cancels out the other meters. So the wavelength result is in nanometers. So you end up getting 6.9 times 10 to the minus 24th nanometers. That's a really small wavelength, but again, it's a ping pong ball. It's such a small wavelength that it's almost like, you know, not long enough to see. Okay, so with macroscopic objects, they have really small de Broglie wavelengths. But at the quantum mechanical world, on the quantum mechanical scale, okay, these wavelengths actually result in energy differences of the electron. All right. Okay, so all right, so excuse me. So any questions at this point? I know it's kind of all new, all right, but this is where it gets exciting. Now, if you look at a wave, if you send a wave-like particle or a wave of light through a slit, it shows something called a diffraction pattern. Whereas if it was just a beam of particles, some of the particles wouldn't make it through the slit, but others would. Okay, and they did a famous experiment called the double slit experiment, where they took a light source and they sent it through two slits. And because these waves because the light behaves as a wave, as the waves are going through these slits, some of the waves do something called constructive interference, where the waves become in phase with one another and they result in a higher amplitude beam. And this is where you get these bright spots on the screen behind the slits. And then you get other waves that do what we call destructive interference. And so that causes the wave fronts to be out of phase with one another and they cancel out. And that's where you get these dark spots on the screen behind it. Okay, and so that showed that light also behaves as a wave. But they're like saying, well, you have this idea that electrons are particles, but they're also waves. Where's the experimental evidence that electrons behave as waves? Well, here's the experimental evidence. They then sent electrons through the double slit instead of light, and they saw the same sort of diffraction pattern that they saw with light waves. Okay, there you go. There's your proof that electrons behave as waves, not just particles. All right. So they call this the double slit experiment, and it was the experimental evidence that we needed to confirm that, oh yes, electrons behave as waves. Now what they also showed was that if they used a laser beam to strike the outgoing electrons coming out of slits, the diffraction pattern disappeared. Okay, and what happened was that you just saw two white streaks that showed up instead of all these diffraction pattern lines. What was going on there was that when the beam strikes the electrons, their momentum changes, and it's just now the light scattering off of those electrons that are hitting where the electrons should have been hitting. Okay. So what this showed was that you can observe the wave nature of electrons while at the same time observing their particle nature. So this shows the particle nature of electrons. Okay, clearly we've got two outgoing streams of electrons, and the light's scattering off of those, and you're seeing this pattern. Okay, but you can't observe both at the same time. Okay, and so this comes up with the uncertainty principle. We're all uncertain about a lot of things, but this is the mother of all uncertainty principles. So Heisenberg in 1924 developed a mathematical relation to describe why we can never observe the wave and particle nature of electrons simultaneously. And if you ever watch Breaking Bad, this is where the name Heisenberg came from. All right, he didn't just adopt it because it sounded cool. This is where it came from, because Heisenberg was one of the grandfathers of quantum mechanics. Okay, so he came up with this equation. Okay, and what it is he's saying, well, the uncertainty in a particle's position times its mass times the uncertainty in its momentum and its velocity is greater than or equal to Planck's constant divided by 4 pi. Okay, and there's uncertainty in a lot of things in life. It's baseball playoff time. There's uncertainty in how the umpire calls a strike, for example. How certain is the umpire that the ball pitched was indeed a strike, right? There's all kinds of situations like that. Okay, so we can do this sample problem next time, okay, but we'll leave off here. But try to stay certain about lab today, okay?